So this is just to show you a very simplified version of what is going on in the Aplysia. In reality, it's much, much more complicated, and it also involves changes at the motor neuronal level. But basically, this is what I've just been talking about, that at the short-term level, you have the 5-HT, the serotonin, being activating the adenylyl cyclase, leading to increased levels of cyclic AMP, which activates the protein kinases, which are then being responsible for closing the potassium channels, leading to increased calcium. At the long-term stage, you have also, and more or less simultaneously, phosphorylation of CREB1, CREB2. So CREB2 is being removed, CREB1 is being activated, leading to production of new proteins required for growth of the synapse. So that's the simplified version. It's in reality much, much more complex, but I think this is the essential. Then you can put in lots of other pathways. There are other pathways which have been described, which work in parallel with this. We're going to come back to a few of them, but essentially this is what it is all about. A secondary messenger being activated through these metabotropic receptors, leading to basically phosphorylation of compounds internally in the cell, which simultaneously leads to interaction with the receptor, thereby leading to short-term changes, and at the same time being transported to the nucleus, leading to long-term changes. So what is essential here is that there's also a basis for what you could call short-term memory and long-term memory. Short-term memory being the immediate changes happening in the transmission across the synapses, the long-term changes requiring protein synthesis and changes in transcription of genes at the nuclear level. So there's a link between these two, and it turns out that it's the exact same mechanisms, secondary messengers, which signal both the short-term changes and the long-term